Good morning. So, how was the keynote? Good? Did you enjoy it? Yeah? Coffee stopped up? Okay, because we have a full-on session for the next 1 hour. I am Poornima Nayar, and I am a software engineer and solutions architect at Particular Software. Heard of N-Service Bus? N-Service Bus? Yes. So we build N-Service Bus and the entire platform tooling around N-Service Bus. That's what I do for a day job. And I get to do a lot of fun things like this, presenting to you all, educating you all on messaging and all great things about technology. And I also run workshops. Yeah, I do all that. I have traveled in from Berkshire, UK, and I'm so delighted to be in Copenhagen again. And if you want to reach out to me on about any questions that you have, you can always do that at Poornima Nayar. That's my LinkedIn profile. Feel free to connect with me. And of course, if you have any questions straight after the session, stay back and ask me. I'm all happy to take questions. You will find me in the main conference area for about next 4 hours, because after that I have a flight to catch. Before we go ahead, let me understand the layout of the room. How many of you are using messaging in some format at this point? Okay, great. And so that's good to hear. Publish, subscribe. So this is the foundational stone for event-driven architecture. When teams usually move from, say, a monolith or a modular monolith, or HTTP-based services into messaging, it's usually publish, subscribe that they start with. It is a communication style. It is something that is easy to understand, but don't get me wrong when I say this. When people or teams move from HTTP-based systems to messaging, it's like a big bang rewrite. Often it's not. There are migration paths in place for that, but teams go through this process. So what is a publish subscribe? You have a publisher that publishes messages into the broker. Then you have the subscribers. You might or might not have subscribers for a message. If there are subscribers who are interested in what the publisher is publishing into the broker, they subscribe, and they all get, each of the subscribers get a copy of the same message. Publisher and subscribers are completely decoupled in time and space. If subscribers are down, the publisher can still function. In fact, subscribers don't know about each other. Publisher does not know about the subscribers either. It does not even know whether there are any subscribers. So the way the message communicates or message gets transferred between publishers and subscribers, or a sender and a receiver, that is PubSub. It's a communication style. Now, talking about the messages themselves that gets published, the word is published into the broker. They are called events. It is a specific type of message that has a specific intent. And the intent is, I am letting the world know of something that has already happened. And because that something has already happened, it is immutable. It is unchangeable. It is a fact. And it should never be an instruction either. So if you have an instruction that is kind of hidden and disguised in the form of an event, then that is an anti-pattern. You have exactly what is called as a passive-aggressive event. For example, I love my handbags. So if me and my husband are walking past a shop, I notice a handbag and I say, you know what, Krishna, I like that handbag. That's fine. That's a fact. It's an event. But what if I say, Krishna, I like that handbag? And then I expect my husband, more than just nodding, to actually go into the shop and then purchase that handbag for me. That is a passive-aggressive event, because I am disguising an instruction inside my event. It's not just a statement or a fact at that point. So events, these are the messages, and events should always be something that notifies the world that something has happened. Should never be an instruction. When you think about publish subscribe, why do teams move into publish subscribe, and what do they get as benefits? Decouple services. We do not have the requirement that the publishers and subscribers should be up and running, be available 24/7 for the system to work correctly. I have published an event, the receiver or the subscriber will pick it up later when it has got a chance. That is the fact. So you have decoupled services, which means that services can be scaled not just vertically by adding more resources to the same service, but you can scale it horizontally as well. That is something that you get straight away out of the box when you have decoupling. And when I mean decoupling, it is temporal decoupling that I'm talking about here. We can reuse events. So suppose you have 3 subscribers to the same event. What if you want to bring in the 4th one? You bring in the 4th one, you subscribe to the event, and from that point, the subscriber starts getting the same event, a copy of the same event from the broker. So you can reuse the same event. This means that you get a modern evolving architecture in your system where adding a new integration can become faster and easier. As long as all the subscribers and the publisher, they all agree upon the contract schema. In our case, the event is the contract and it should follow a schema. So when you look at it from the theoretical point of view, teams achieve autonomy. They can build faster, scale faster, deploy features faster, and you can have separate release cycles and clear ownership boundaries. That's something very important. So once you are into the PubSub world, teams can even bring in and then reroute the message into a completely different service as long as you have that event in place, a subscription in place. You want to swap out implementations? Possible. So that is all benefits at operational level with publish subscribe as well. So all this sounds a very elegant solution on pen and paper, right? So it checks all my boxes, and I'm so happy that we've arrived at this position. So this is where teams start settling down and think that, yeah, PubSub checks all my boxes. This is enough for me, and I'm just going to settle down here and then let the system run. But then you start noticing cracks in your foundation once you have hit production. You have a solid foundation in terms of messaging and publish subscribe. But when you settle down just at publish subscribe and don't think beyond that any further, that is when you have the cracks in the foundation and cracks in the building. And the saddest part, you notice it when you get into production, or even before, when you have done a lot of development work. So let us go and talk about our order processing workflow. Why? Because this is something that is so kind of familiar to all of us, and so the domain comes across very easily, and it's easy to communicate the concepts. So this order processing workflow, we have an order that accepts an order service that accepts an incoming order from, say, the web front end. It creates the order and publishes an order created event into the broker. The inventory, the payment service, the fraud check service, and the shipping service, they all subscribe to the same order created event. And they might be going and creating local records and doing their own work. So all subscribers react independently. That is one aspect of publish subscribe. So we have publish subscribe in place. Inventory then says, yeah, I have done my work, let me publish an event. Payment says, I have done some work, let me publish as well. Fraud does the same thing. Shipping might be watching for each of those events and subscribing to those. The order service also might be watching out for each of these events published by the various different services so that it can try and understand where the order is. And finally, it says, you know what, I think the order is ready to be shipped. At which point, shipping comes in and says, yeah, I can start shipping the order, and then completes the workflow somehow. So we have a lot of boxes and a lot of arrows coming in and out of boxes, yeah? Stay with me on that. But we have a lot of assumptions at play here. That order service box, what is the guarantee that it can consistently publish the order placed event? What I mean is that for every incoming order, how can you make sure that there is one order created in the database and one event published? Remember the fallacies of distributed computing. The network is reliable is an assumption that we make, and that assumption is at play here. Everyone receives order placed. That's an assumption as well. Why? Because once that order placed event is published into the broker, what if fulfillment is, the fraud service is down or the payment service is down? The order placed is not going to reach all the subscribers all at the same time. It is possible that something is restarting. If you have a message loss scenario, that is something totally different to be considered here. But again, this is a solid assumption at play here. Events arrive in order. That is a big, big, big fallacy. Events never arrive in order. In fact, if you have something in order, then you are very lucky. That is fluke, because network is not reliable, bandwidth is limited, and there is always latency in networks when it comes to distributed system. When all these fallacies are at play, they are like gravity. You cannot defy them. So there is absolutely no way that events arrive in order. And if events arrive in order, you are having a very good day. And that assumption can really cost you on a bad day. What about retries? So retries is something that is spoken about with messaging, right? The very fact that you have a retry, which means that there could be side effects. What if you have a retry and then it duplicates the side effect? That's also possible. And looking at that order processing workflow, does the order service or any service know enough about the actual order itself? Where is the order? Can anyone say with absolute guarantee that this is where the order is at? The workflow is spread thin across the subscribers. I have to go and work out where the order is at by talking to various different services. Detective work, right? One of the biggest assumptions, again, is that there's no alternate paths or compensations. Businesses always work with compensations. We have an inventory service. What if for an order, you can only reserve part of the inventory? Or what if inventory is not available? How do you compensate? Do you straight away refund? This is a gray area, right? Payment has succeeded, fraud check has succeeded, but inventory, I could only reserve part of it. That's a very gray area that needs to be accounted for somehow, and you are not accounting for it through just a button click. That button click is driven by a business decision. You know what? I can back order this. That is a business decision at play. So there's always alternate paths or compensations. How is the system going to self-correct it and put it back into place? That's something we need to account for. Finally, emergent failure modes. This is a big thing, because when you have events firing off in every other direction from your system, so you have a publisher that publishes, subscribers, they consume and publish more events, and every other subscriber is adjusting itself by publishing and subscribing to more events. So you're working off raw signals here. There could be 101th event, which you might not have accounted for because it has come out in a way because something arrived out of order, something happened the way it shouldn't happen, and that is a workflow or a state which you might not have seen or thought or accounted for before in your system. Then you have your system in an inconsistent state. So these all are caused by raw publish subscribe in place when you have too many raw signals and you work of raw signals. Finally, the biggest benefit that we had, the operational benefit of bringing in a new service and then reusing the event. The minute you bring in a loyalty service here, it needs to start subscribing to every other event possibly from the rest of the system. Every other service might have to change accordingly as well. So we are back to square one with a distributed monolith in place, which is even worse, right? So this is where you hit your PubSub plateau. You cannot really move further. You've got things wrong. Because when you have multiple consumers that react to the same event independently, the independently is very important here. I might be subscribing and reacting to an event in a very different way that another subscriber could be. So we are reacting independently. When you have multiple subscribers reacting in an independent manner, all these are questions that you should ask yourself. How do I even save data during crashes? What can I do about it? Who owns the workflow? What happens if a consumer fails, right? What if events arrive out of order? That's a big thing. What about consistency guarantees? What about slow and overloaded consumers downstream? and compensating actions. Businesses always have compensating actions. But publish subscribe does not give you answer to any of this, because publish subscribe is all about temporal decoupling. That is what it gives you. Everything else is built on top of that. Because publish subscribe is ultimately a communication style that I told you about. It's not something that you can use for system design. So let us now talk about, so we have understood what problems you can face. Now we can look at the problems that you face in reality and solve some of them and learn some patterns on how to solve some of them. So the first one I want to talk about is the dual write problem. So one of the most common challenges in a system is when you have the need for consistency between your business data and the message publishing. How can you ensure that for every action, there is exactly one message that goes out into the broker, and there's exactly one side effect? But the problem here is that when a system tries to write into two different boundaries, the database and the broker, there can be inconsistencies. How do we solve this? So the problem here is we have the system on the payment service. When the order created message arrives, it tries to write into the database that the payment is taken. And then if the payment is succeeded, it tries to publish an event as well. But what happens if there is a blip in the network between saving the data and publishing the event? What we have is then what is known as a zombie record. You have a record in the system, but none of the downstream subscribers or rest of the system knows about this at all. So what happens? The order is probably stuck, and you have an angry consumer. And the second scenario could be, I have changed the order. As a developer, I've said I will actually publish the event first and then save into the database. Again, a network blip can happen, but then the case is I have let the entire system know that the payment has been taken, but the payment has not been taken. There's no record of it. So again, the business is actually losing out money. Maybe the business is losing credibility in the long run as well. So this is a scenario that can happen, and it's a very common challenge in distributed systems. So most data loss in distributed systems does not happen in the message broker. Message broker is usually a highly available infrastructure. So is your database. But between these boundaries, that is where the data loss happens. And that is because we have two independent durability boundaries, and the two operations, they are not atomic. They do not fail and succeed as a whole. They can fail or succeed as parts. That's what we've seen, right? So how can we solve this? Sorry, the bright lights are really making me sweaty. Can you dim the bright lights? Oh, thank you. That's much better. So the transactional outbox pattern. This is essentially an infrastructure in place. Infrastructure in the sense it's not a physical or a cloud infrastructure. Code can also be infrastructure, right? Because it is a reusable kind of thing. It is an infrastructure that guarantees consistency between your business data and messages. So with transactional outbox pattern, we say that, you know what? We are committed to having the business data and the messages being consistent as a single thing. So we will worry about the broker later. And we do that by saving the business data and the messages to be published or the messages to be sent in a single database transaction into a database. And that database is usually your business data, your database where you store your business data. So the message is not sent out immediately. It is saved into the database, and then the infrastructure comes in and then sends that data out. How? So in the payment service, when there is an incoming order created event, the infrastructure kicks in and begins a transaction. And then as a developer, our code comes in, where we handle the incoming message and save the business data. So that is the only code that we write as developers. Everything around it is provided by a messaging library. And once the handle incoming message is done, when we actually publish or send the message, That is when the infrastructure comes in and says, I will store all the messages in the the Outbox table, which is a separate table in your database which holds all the outgoing operations, because I know that in this service there's Outbox enabled, and I will commit the transaction. So no matter what happens, your business data and messages get stored in a single atomic transaction into the database. And then it moves into the sending of the message operations itself. So the data is stored in the database, the message is stored in the database, there's something running in the background, again the infrastructure, which tries to send out that message. And then it says, hey, you know what? That message, I have tried to send it, it succeeded. I'll mark the outgoing operations as done. And then I'll acknowledge the incoming message so that the incoming message can be marked as processed and then removed from the broker. So this is phase 1 and that is phase 2. But what if there's a outage, or while acknowledging the message, the receiver crashes? That is something that we need to think about, right? Because Outbox is all about protecting the publisher. This is to achieve consistency and make it more reliable. It cannot actually cater in for the scenario where there's an outage while processing the receiver and the message reappears. Remember, brokers are always on at least once delivery, at least once message delivery. So this is where idempotency kicks in as a concept. So with NService Bus, you have Outbox plus idempotency as a single thing in Outbox, but with some of the other messaging libraries, you might see it as Outbox and Inbox, or Outbox and idempotency, for example. So idempotency is what ensures that processing a message multiple times has the same impact as processing it only once. So multiplying a number by 1 is the scenario here. So some operations are idempotent by nature. Some you can have idempotency, or some you know that for this specific message type, this is the side effect, and I can check for that. But that is getting into the processing stage of a message itself. But a more generic way to do that is deduplication. This is what is baked into something like mass transit or NService Bus when you start using Outbox pattern. So with deduplication, we check whether the incoming message has already been processed. So you know the outgoing messages that the system tries to write into the table, that is stored in the database against the incoming message, correlating it together. So if a message has been already processed, there's a sign of it in the database, should that transaction commit successfully. So with deduplication in place, the payment service, with every order created message that comes in, it goes through the process of deduplication. And if a record is found in the database, that is, there's proof that the message has already been seen, you begin the transaction and goes through the phase 1 completely, and then moves on into the phase 2. If there's a record already there, in our instance, it might be there because we crashed at the point of acknowledging the incoming message. So there could be a message already. So in which case, it moves on into phase 2 and tries to send the outgoing message according to this workflow. So if the outgoing message has already been sent, it'll get sent. Otherwise, it'll just acknowledge and move on. So in our scenario, all what is going to happen is acknowledging the message. But outage can also happen here in the mark the Outbox table row as sent. So which means that the message could be sent out again. So which means that the downstream services which accepts those or subscribes to those messages that are sent out by the service needs to have deduplication in place as well. With me so far? So best practice, every service that has state change and publishes event should have transactional outbox. And you might have heard that transactional outbox plus idempotency gives you exactly once processing. Outbox is all about exactly once processing is something you might have heard. You know what? It's an illusion, I'm telling you. All what it is doing is at least once delivery of a message from the broker plus idempotency. That is what is giving you the illusion of exactly once processing. And you might be thinking a transactional broker can do this, right? No, a transactional broker can never come in and step in for your business data. So Azure Service Bus, for example, transactional broker, it can make sure that an incoming send and incoming message and outgoing sends all can be wrapped up in a transactional operation, for example, but not with your business data. You need Outbox for it. So save your business data and save your system using Outbox. But Outbox cannot do any of this. It's not about exactly once delivery. It does not tell you that, hey, I can perform without idempotency. It cannot orchestrate event, and it does not make your events better. You have passive-aggressive event, it will handle the passive-aggressive event for you. So Outbox is all about making publishers reliable, and it actually ensures or it enforces the need of idempotency in your system. So talking about orchestrating events and workflows, back to our order processing system, if you look at this system, is there any place where we can say that, yeah, this is where my order is at? No, it is spread thin. Can you say what is done and what is left to be done? Probably not. Every service is handling raw signals from every other service. And when you have that kind of a system in place, what you have is pinball architecture, where you have a lot of publish, subscribe, and events going on, and that is turning into your system into a bouncing ball of events. Every service reacts, emits events, every other service reacts, and the saga moves on and on. Over time, what happens is you have a lot of arrows going in and out of the Outbox. You get unintended side effects, race conditions, performance issues, and such a system is a nightmare to debug. You need Sherlock Holmes again. That's what you're all going to be if you have just PubSub and so many different services and so many arrows coming in and out of your system. But what can help us here is long-running workflows. Think about an order and the lifetime of an order. Is it going to be happening instantly? No. Even the best system takes about milliseconds to process, and then even if it is a digital product, it takes a minute or two to arrive in your email. And if you're looking at a physical order where you have physical things to be delivered to you, it can take probably hours if you're on Amazon Prime same-day delivery, to even days or weeks or months, probably. Reality, right? So why do we actually need to force a workflow that is synchronous into something that is by nature asynchronous and takes over days? There's no need for that, right? What we need is long-running workflows. We have multiple services that needs to step in, multiple databases are involved, so there will always be time involved. So that is where long-running workflows come in from. So you might ask, why not distributed transactions? Because it is all about handling consistency across multiple databases. So distributed transactions gives you atomicity across all services, all or nothing outcomes, strong consistency, everything that we are looking for. But you have tight coupling, always available as an assumption. It is fast, it is homogeneous, it is under the control of a single team, all which are the signs of a monolith, not a distributed system. And distributed transactions itself, they do not map to the business reality. Businesses don't think in terms of rollbacks. Once you want to refund an order, it is a refund of an order. It is not a rollback of an order. Refunding is a business decision. Back ordering inventory is a business decision. It's not a rollback. So there's no mapping to the business reality when it comes to distributed transactions. And there's two single point of failures: the coordinator, the distributed transaction coordinator itself, and time. We are assuming that the coordinator will be fine, the participants are fine, they'll show up on time, and they'll say yes or no on time. All are assumptions. We need to get rid of assumptions, and we need to map to business reality of a workflow, and that is what we are going to do with our long-running workflows. I'm going to talk about sagas, which is an implementation of workflows in N-Service Bus. It is called State Machine in Mass Transit, and it's called Saga in Wolverine as well. Everything follows the same pattern. This is not to be conflated with the Saga pattern paper itself. We call it sagas, state machines in mass transit, or Wolverine also calls them sagas. So sagas are essentially stateful message handler. So in a normal pub sub or a send or receive scenario, when you handle a message, the receiver just handles it statelessly and then moves on to the next task. It does not store information of what it has done. But sagas can handle multiple messages, and between handling those multiple messages, it can actually store the state into a persistent storage, might be SQL Server, might be Cosmos DB, whatever, and say that these are the things I have done so far. So the decisions it has made, the tasks it has done, it is stored somewhere for you, right? So what makes a saga? So the persisted saga state to begin with, and that is loaded into memory as saga instance. So the persisted saga state is basically a memory of what decisions has been made and what is pending. And it is persisted durably at each step of message handling. It might be handling 5 different messages, a saga. At each point of handling each of those 5 different messages, the state is stored. What has been done is stored. And saga also knows what is to be done as well, right? Then there's the saga behavior, the behavior that moves the workflow forward. With every incoming message that is handled by saga, some work is done, some messages are published, some instructions are given. So at each step, saga moves the workflow forward. And because we have set behavior, it is going to prevent the invalid state transitions and make sure that devoid of distributed transactions, no matter in what order messages arrive, I am going to course correct, and then I'm going to put the system back in a consistent state. Yeah, so saga is here, and it comes it finds a message incoming. Yeah, I'll handle it. But you know what? I know that this process also needs the other message. Have I processed that other message? That decision or that memory is stored in the saga state. And if it finds that that other message that I'm looking for has not been processed, yeah, I'll make decision accordingly, and then I'll try to see at the end that it is all put back in correct place. So it is like go in a straight line, or go that way, or go that way. At the end, the destination is the same. The workflow is completed. There's a finite state that is order completed or order cancelled that saga tries to arrive at a decision at the end. And all the course corrections needed, backordering inventory, refund for a part of the order, issue a discount, all these are decisions that sagas can do to do the course correction and reach the destination at the end. But we also need some correlation logic to make sure that each incoming message is correlated to an instance of the saga. That is needed. And the completion logic. What is the final destination of this workflow? For example, would be order cancelled or order completed. Both of these could be a final state. So, am I at a state where I can complete the order? Am I at a state where I can say that the order is cancelled? That is the destination set by saga, and it tries to course correct. So it is a system that is course correcting itself till you reach the destination. So putting that all together into a flow diagram for every incoming message that is handled by a saga, it uses the correlation logic to check whether a saga instance exists in the storage and then load that instance up. And if it is not found an instance, it tries to start the saga. And then, as a developer, you would process the message. Again, as before in Outbox, Saga is like an infrastructure, a code infrastructure that is provided to you by your messaging library. What you would be doing as a developer is only handling the process, handling the message, processing the message using some predefined business logic. It involves making decisions and suggesting next steps. Saga does not itself, should not do any business logic. It should only make decisions, and for those decisions, send out other commands or publish other events. At this point, we can check, or the saga can check, am I in a position to complete the saga using the completion logic? If the saga can mark itself as complete, then it completes the saga again. Completes the saga. Or if it is at a position where the final destination has not been reached, it tries to save the saga. So for the next incoming message, the same process repeats. It keeps on repeating till the time where the business decision or the destination of the order has been reached. That is order completed or order cancelled. There are two ways of achieving saga. One is orchestration and the other is choreography. This is a 1-hour topic in itself. It's extensive. But understand that workflows can be choreographed or orchestrated. With orchestration, you have a central orchestrator that instructs specific services to perform specific actions. So it's like a project manager who manages the whole project and makes sure the destination is reached, right? So with orchestration, the rule of thumb is that the saga sends commands when business decisions are made, and it receives events to keep the workflow moving. So it handles a lot of messages. But the workflow is centralized. You can actually look at this orchestrator and say whether what is the state of the order. So a customer success representative, when someone rings in, can look at some read model attached to the saga, the orchestrated saga, to actually tell them what state the order is at. That is what is orchestration. But beware, the orchestrator can become a monolith if you're not careful about it. So it's very, very important to make sure that there is no business logic creeping into that orchestrator. It is only for handling the incoming events and then making the business decision and then trying to complete the saga. It's all about course correction, absolutely no business logic. The only data that a saga should interact with is its own data stored in the persistence. That is the saga data. So with the orchestrator in place, the workflow can look something like this. So there would be a central orchestrator going through the entire workflow. Again, this is a hypothetical domain. In your domain, it could be different. In fact, it is also possible that there are multiple sagas inside the services as well, inside multiple services as well. That's also possible. There could be a sales process manager. There could be some kind of a workflow happening inside fraud as well, inside shipment as well, inside inventory as well. That's all possible. You can have a central orchestrator and then sub-workflows in the system according to your domain. Absolutely possible. Choreography. So if you're using PubSub, publish subscribe, this is what you get out of the box. So like I said, publish subscribe is all about how the messages reach the subscribers. The reacting independently part of the subscriber, that is choreography. Services react to each event to complete a sequence of steps. But that sequence of steps is spread thin. Only a specific service knows about this sequence of events. And it is usually event-driven. There's no central coordinator, and workflow is within each service. So in our domain, the order processing workflow, things don't change so much. What we have is already choreography in place. Now, there can be a question of orchestration versus choreography. What can help you in making that decision early on is looking at your compensating actions. If you have a lot of business decisions to be made, a lot of arrows going in and going out of each of those boxes, that means you have a lot of business decisions, and that is a sign that you might need an orchestrator. So think about the compensating actions that can actually tell you whether you need to go the orchestrator way or the choreography way. Now, when you have compensations and compensating actions, they should also be treated as first-class workflow states. Because if refunding is a compensating action, understand that refunding can also fail. So always treat it as a workflow, a first-class workflow state. Now, often in systems, it's not orchestration versus choreography. They can completely coexist. You need to understand at which service boundaries you need orchestration and where you need choreography. In reality, you might need both in your distributed system. But as a rule of thumb, choreography is for independent reactions where things can be absolutely independent, and orchestration when you need decisions to be made. A set of questions that can help you when you are thinking about your distributed system, about choreography and orchestration is, are there too many services reacting to too many events? Is the final state ambiguous? Can a specific service own what the final state is. Order complete or order cancel or order refunded, which service actually owns the state of that order? If the final state is ambiguous, then you have decisions to be made, and then which means that you need to lean into the orchestrator. If you have compensation logic that is spread thin across the services, that is a sign that you need an orchestrator. Events arriving out of order, if it can topple up your system, you probably need an orchestrator to course correct and put your workflow back in place. If you have timeouts, say for example, I only want to place an order 20 seconds after the user has actually placed it via the website. Why? Because I'm giving 20 seconds to the user to make a decision themselves whether I have made the right decision as a user to buy something. Buyer's remorse. I often have that when I purchase handbags of the website. Again. So I get 20 seconds after I click the button, place the order, to actually cancel the order. That's a real use case scenario. If replaying one event can trigger unexpected reactions across several services, that's a sign that you've got something wrong. If you need a full event chain to understand basic behavior of a system, oh my word, then you have got things wrong already. And something very important, inventory reservation failed. Would it mean different things for the business once the payment has been taken and before the payment has been taken? Are the actions going to be different before the payment has been taken and after the payment has been taken? Then you probably are looking at orchestration again. So these are two different patterns. I usually fit in scatter-gather as well, but I think that might be too much. So I'm going to not talk about scatter-gather, but if you want to speak about scatter-gather, come find me after the talk. I'll be happy to talk to you. But we'll go into some of the more operational aspects, just because I want to leave some time at the end for question and answers. Usually, on a happy, normal day, your system might look something like this. There might be orders pouring in, and it might be a happy day where the receiver keeps on processing at a normal rate and your throughput is kept up. But what if you have that Black Friday sale? Because Black Friday sale is very, very famous in UK. And then you have stampedes and you have sites crashing. That's a reality. So Black Friday sale day, how do you keep your throughput constant? How do you make sure that the orders are being accepted into the website? Because that's the first thing to be done, right? Orders need to be accepted into the website, into the system, and then the rest of the system can then process at a normal rate. What would the system look like, and what do we want to do on such a busy day? Scaling out the consumers. The receivers can be scaled out into multiple physical instances, looking at the same queue, so that the throughput is kept at a much higher rate than on a normal day, and there's orders being accepted into the system. So this is known as the competing consumers pattern. This is one of the first or the early things that you learn when you learn about messaging as an architectural style. Remember the horizontal scaling that I spoke to you about as a benefit? That is this, the competing consumers pattern. So you have multiple concurrent consumers reading from the same queue, where each message is processed only by one consumer. So the broker makes sure that when a receiver is processing a specific message, that's the only receiver looking at that message. Usually brokers lock that message during the processing time. That is the normal or the behavior that I have seen across most of the brokers out there. But having a queue is very important because the consumers are literally competing for messages from the queue in this instance. And it is seen as the simplest and the most effective way to scale throughput. This is one of the first things that you do when you need to build up throughput in your system. So it's a scaling pattern, effectively. So with our competing consumers in place, for example, on inventory, it can look like this, multiple physical instances of the inventory. You could also have multiple physical instances of the order service as well. Why? Because that's the first point of entry into our entire distributed system. I have put the inventory on a competing consumers as well because I need to make sure that with the incoming messages that I have for orders, I don't want to run out of inventory. Maybe a product is very, very popular and it is selling out like hotcakes. I do not want to run out of inventory and then not have the website reflecting that at some point and customers turning back off from the website. We don't want that. So again, business decisions to be made on where the competing consumers pattern should appear. This is just a hypothetical situation that I'm giving you. Now, pub/sub versus competing consumers. Pub/sub is a communication style. Every subscriber gets a copy of the message, and it is a style that is optimized for extensibility and broadcast-like scenarios. Whereas competing consumers, it's a scaling pattern. It is a part of the wider picture of back pressure and flow control. It's a much bigger thing, and competing consumers is one of the aspects of that. Here, consumers are literally competing, like the name says, for messages, and each message is then only processed by a single consumer. This is optimizing for throughput and elasticity in this case, right? So if I am to demarcate between the two, pub/sub is all about saying, who is interested in knowing something has happened? That is pub/sub. Competing consumers is, who should work with this? Or who should do this work? That is the difference. That is the two different questions that the two things are trying to answer for us. But the two can work together only if you have an AMQP-based broker. So you can also have MQTT as a protocol, where you consume directly from the queue, but competing consumers always require a queue. So AMQP-based broker like Azure Service Bus, it publishes into what is known as a topic, and at the end of the topic is subscriptions, which is like virtual queues. So you would then have your multiple instances of the inventory service looking up into the subscription, the virtual queue behind it. If you only have topics, you cannot have pub/sub and competing consumers together. You need the subscribing queues. But when you use competing consumers, understand that there is no ordering guarantee, absolutely none. If you have dependency between tasks, do not use competing consumers. This is best for do a job once kind of scenario. One of the biggest things that you need to consider is you are accepting a lot of orders from the website, for example. The order service is scaled out. If you have tens and thousands of orders pouring in on a day per minute, then you're putting the database at stress. That is something that you need to be mindful of. Can the database handle it? Because if the database cannot handle it, there's no point. You have already made your order service crash. And because it's the closest to the consumer, they might see the outage too, or they could be impacted. The entire throughput of the system then suffers. Always have a retry policy so that failed messages do not impact your throughput. We will talk about retries in a little bit, but one thing to be aware of when you retry with competing consumers in place is that the retry can jump from one consumer to other. So initially, it could be retried on consumer 1. Because it failed, it goes back into the broker. The next time, the retry could be on consumer 2. That's a thing that you need to be mindful of. So at this point, I would like us to think about this ancient proverb. An unchecked flood will sweep away even the strongest dam. In our case, the unchecked flood is the huge influx of data that is coming in. And the strongest dam is what we think is really strong, our system. But you know what? On those busy campaign days, things are really, really busy, and we need to make sure that our system survives the pressure. It adapts, it's resilient. And that's where the picture of back pressure and flow control comes in from. So competing consumers keeps up the throughput, then impacts your downstream services. Back pressure and flow control is the resistance from this side to make sure that, hey, slow down, the rest of the system cannot keep up. Let us just put some resistance in place. That's back pressure and flow control in the simplest of the terms. So it's like speed. Speed thrills but kills, right? Without back pressure, what you have is unbounded throughput that welcomes unbounded failure. We do not want that scenario to happen. When you have back pressure, it is like a controlled resistance to incoming work. So back in the UK, what we have is a system called smart motorways, where if things are really busy, the motorway adapts. So instead of 70 miles per hour, then we all get to see 50 miles per hour maximum speed, so which means the traffic has to slow down. But then what happens? There's lesser chance of crashes, which means that even at a slow pace, traffic is moving, there's no accidents closing the lanes, so things are still moving. There's some resistance. I might not be able to drive fast, but you know what? I'm safe. I'm going to reach the destination on time as well. As a whole, it works. That's the whole point. So back pressure is all about slowing down and succeeding at staying alive. This is that resiliency aspect of messaging. Even under pressure, I can actually adapt. Failures are normal. Yep, I have recoverability. I accept that failures can happen. But even when failures happen, I have recoverability, so that is the fault tolerance aspect of it. But under pressure, I can stay alive. This is the resiliency term that is usually associated with messaging. So what are some of the patterns that you have when it comes to having back pressure? We can start with consumer-side throttling. So limit how many messages an endpoint can process concurrently. So limiting the amount of concurrent processing. So if that prevents actually, you can use this when an endpoint is overwhelming its database. So the competing consumers pattern, when it starts to overwhelm the database, when you have signs of it, consumer-side throttling can help. Now, rate limiting with some automation, the automatic. So this is limiting the calls to a dependency. Not every consumer is connected to a database, right? A competing consumer can also reach out to third party. So we should not overwhelm that third party. So that can be had as a check in place using the automatic rate limiting. Now with N-Service Bus, what we also do is if you have a lot of messages from the same endpoint hitting the error queue, we arm the circuit breaker on the endpoint itself. So that also acts as a rate limiting technique in place. Now, rate limiting is usually used in conjunction with circuit breakers. So you have a dependency that is struggling. You are sending a lot of messaging into it. Of course, you rate limit on this side, the sending side. But on the receiving side, if say it is another receiver that is then reaching out to a third party, this endpoint can arm its circuit breaker, completely stop itself from accepting messages. And that can be for a short period of time till the overwhelm is done with, till the dependency is active and healthy and not struggling. Bulkhead. This is isolating elements of applications into pool so that if one fails, the other continues to function. This is very important at system design time when you design your endpoints. Maybe the create order command that comes in from the front end, which takes in the order from the user and places the order, that is something that needs to scale a lot. But then if you start putting in all the other events that is to be handled in the same endpoint, remember, you are not just scaling the endpoint for the create order command, you are also scaling for all the other events that are handled by the service. Do you really need that? Think about it at the design time. Queue-based buffering. This is something you get out of the box without even doing anything the minute you introduce messaging into your system. There's a lot of message coming in. Fine, I can buy you time because the queue is absorbing the pressure. But then why do we need the other strategies? Queue size. Queue size is something that is controlled by the disk space. Even if you think about Azure Service Bus, there's a finite disk space. SQS does not have the problem of that. It is infinitely sized queues. But then having a lot of messages in the queue is also not a good thing. That is a sign of your system under stress not being able to keep up. So that's a very important metric when you come to messaging as an architectural style in a distributed system. Retry strategy with jitter. So you have 10 different services. Maybe you have had a massive outage and then you are starting to retry at one endpoint, starting with the service, the order service. Say you are retrying 10,000 different messages on the order service. Everything downstream will also feel the pressure because 10,000 will lead to another 20,000 messages that are retried across the board. And if you start retrying everything at the same time, what you're gearing up is called a retry storm. That is DDoSing your system using a retry. something that we don't want. And that is where you can introduce a jitter, a system-wide kind of staggering to make sure that this retries first, this retries later on, the third one retries like a 10 seconds or 15 seconds later on. That's also possible. Load shedding, something you don't want to do, but it can be useful if you want to deprioritize some messages. Probably I don't want to calculate the loyalty points straight away. I'll park it for now. Possible. Alerts on the queue depth. This is getting into the metrics aspect, but the queue depth monitoring is so important. Use that observability tool that you have alerts on your queue length. That is an initial telltale sign of how healthy your system is. Error queues and error queue monitoring. I cannot stress enough on this. If you have messaging, the point number 0, the key takeaway number 0 is have error queues, have error queue monitoring, and error queue management. Because that is where all the messages go and sit. You do not want an unstable system because messages are sitting in the error queue and expiring, and there is absolutely no way of replaying that. So this point, I cannot stress out. I cannot stress how much important it is. And finally, talking about retries, it's all about letting time fix the problem. Instead of having a network blip, create an incident and alerting the entire organization that something is off, we retry. Sometimes it might get fixed with time. That is retries. That is what retries is giving you. Design your system for self-healing. So suppose you have a network blip or a database record that is locked. It can be solved using an immediate retry. So I tried, something is locked, it's fine. I'll just retry. So that is the immediate retry where you retry immediately. It is cheap and fast, and it's for transient exceptions like this. A row of database locked or maybe a network blip. But have an upper limit on the number of retries, because the more you retry, the queue depth might be increasing and you're preventing other messages from having a chance to be processed. The second one is delayed retries, where you retry with a delay for semi-transient exceptions. Maybe a service is restarting. Maybe a failover is bound to happen and it is in course. So you need a little bit more time than a network blip to fix itself. So semi-transient exceptions where time can actually step in and fix the problem, you go with delayed retries where you retry at fixed intervals or at exponential backoff. So retry at a 10-second, then 20-second, and 30-second, and so on. But again, have an upper limit on the number of retries, because these kicks in after the immediate retries have been exhausted. And for each delayed retry, there is the configured amount of immediate retries as well. So one message, it can go through if you're looking three numbers of immediate retries and 3 of delayed retries, it can be a substantial number before the next message actually gets a chance to be processed. So this actually might impact your throughput if you're not careful about configuring it. Play with your system, understand it before you arrive at that count. And then you have your systemic exceptions, where it is persistent errors caused by logical errors or a deployment failure or a bug in your system. These causes messages that just cannot be handled by the system. So then you want to move it to an error queue when all the retries have been exhausted, so that then a person can step in, use that error queue as their on-call inbox, and go through what is happening. So that is why error queue management is very important. And then when you have fixed the bug, replay the message from the error queue. Equally important. As a best practice, have a retry strategy, immediate followed by delayed, followed by moving into error queue. And have a retry count as well. X number of immediate retries followed by Y number of delayed retries. Absolute must. Retry storm, beware of it. Don't let your own system DDoS you. For example, if your queue depth keeps increasing and then the queue itself is so filled up, then messages can start to get lost. You don't want that. It could lead to a potential outage of your system. If you are sending 10,000 of requests in a single batch to a struggling service dependency, it is struggling, it is just coming back healthy, it will cause another outage and it will DDoS the system again. So be very careful about retry storms. Finally, error queues. Have the visibility that something is wrong and it contains the error and stops that failure from spreading. With messaging, one of the key benefits that you get is failures are very silent. One part having an outage does not mean the entire system is out, because you have the temporal decoupling. But then, how do you know that your system is unstable? That is error queue giving you the visibility. This is a very, very key takeaway. If you do not have error queue monitoring and management, your system using messaging is incomplete by design. There are different tools available for error queue monitoring and message replay. If you're using the native SDK clients, you can have dead letter queues in Azure Service Bus or RabbitMQ Shovel plugin. Or if you're using a messaging library like Mass Transit or Service Bus or Wolverine, there is a particular platform. I think Rebus has the Critter stack. Then I think, Rebus has Fleet Manager, and then there's Wolverine and the upcoming Critter stack. All these are tools that are useful. So which patterns to use when? This might be an important slide that you might want to look into and take a picture of. Outbox for correctness, sagas for workflow, competing consumers to solve throughput pressure, retries, error queues, and back pressure for the operational safety of your system, and error queue management. Not optional, it is a must-have, not a nice-to-have. Always have error queue management. Can I move to the next slide? If you need to take a picture later on, just come find me. I'll bring up the slide again. So remember, apply the patterns incrementally. Just because you have learned all the patterns, do not apply them in one go. See what you need, see what your use cases. In all probability, Outbox and recoverability together with error queue management, that is the first starting point. Everything else can wait. And if you cannot explain why a pattern exists, remove it. You might have questions in your head. It might be a mess in your head at this point, but that's a good mess. That means you have messages that are in process, in flight, and processing. You will have questions. Don't worry about it. But understand this, PubSub is where you get started. Patterns help you finish strong. And that's a list of resources for you. There is a sample as well, where you can actually see all the patterns that I discussed today as code. That is the AWS Loan Broker sample demo that we have. You will have questions. You will have messages that are in flight and processing. It's a good thing that you have not finished processing yet, which means that if you have questions, reach out to me on this LinkedIn profile as a DM. And then we can continue the conversation. I'll try to answer the questions for you. Thank you.